look up at the night sky. See the stars move across the sky. The moon and the sun do the same thing. They rise and set. It's not surprising that ancient peoples viewed the earth as fixed, and all celestial objects revolved around us. The ancient Greeks, such as Plato, Aristotle, and culminating in Ptolemy, constructed a cosmology with the earth surrounded by a number of celestial spheres that rotated around the earth each day. There was a sphere for the moon, one for the sun, one for each planet, and one for all the fixed stars. Planets were identified as different from stars because they changed their position over time, whereas the stars were seen to be eternally fixed in place. The Earth-centric model stood the test of time for over 1,500 years. It wasn't until the 16th century that things started to change when Nicolas Copernicus proposed to put the Sun at the center of the solar system. In so doing, he put the Earth into rotational motion about an axis, and he put the Earth into revolutionary motion around the Sun, but putting the Earth into motion was hard to swallow for most people. Copernicus's idea didn't really start to take hold until the early 17th century, when considerable evidence for the Copernican model was compiled by the likes of Tycho Brahe, Johannes Kepler, and Galileo Galilei. Tycho Brahe, with mural quadrants, sextants, and his naked eye, used parallax measurements to find distances to the planets. He focused on Mars and tabulated volumes of data on a daily basis. Using this information, Kepler found that the orbits of the planets, including the Earth, were ellipses. And Galileo, using the newly invented telescope, discovered that the Milky Way cloud was actually stars, that the Sun had spots on it that indicated that the Sun was rotating, that Venus has phases like the Moon, indicating that it goes around the Sun, and Jupiter has 4 moons. Imagine how it must have felt when Galileo first saw these moons. All the world believed that everything revolved around the Earth, and here you are looking at moons that are orbiting Jupiter, not the Earth. But resistance to change is strong, and it wasn't until the 18th century that Newton turned the tide for good. We are all familiar with his formula that force equals mass times acceleration. Newton's better understanding of gravity was the key. A good way to view gravity is to think of it as a gravitational field surrounding the object. The intrinsic strength of the field is set by the fixed mass of the object. But as you can see in this illustration, when distance from the object increases, the surface area over which the field is spread increases as well. This effectively weakens the force of gravity felt at the more distant point. We know that the geometry for a sphere has the increase in surface area proportional to the square of the radius. So the gravitational field strength is reduced by a factor of 4 every time the distance increases by a factor of 2. We call this the inverse square rule. We'll see this rule again when we discuss standard candles in our section on stars. It's interesting to note that the constant of proportionality, g, in Newton's universal gravitation formula was not known to Newton. It took another 100 years before physicists had instruments sensitive enough to measure this number. But once we had it, it became possible to measure the mass of the Earth at 6,600,000 trillion tons. Newton broke Aristotle's 2,000-year-old dictum that there are 2 sets of rules for nature. One set for here on Earth, and another set for the heavens. With Newton, we came to understand that there is only one set, and it applies everywhere. In 1752, the French astronomers Lalande and Lacaille used the parallax method to calculate the distance to the moon. Here's how it works. 1. Draw a line from a point on Earth to the moon directly overhead. 2. Extend this line to a distant star. 3. From a measured distance across the Earth, draw another line to the distant star, and another one to the moon. Measure the angle between these two lines. In our example, it's approximately 1 degree. This is the parallax. Note that this line to the moon crosses two parallel lines drawn out to the distant star. From simple geometry, we know that the parallax angle theta is also the angle between the two lines at the moon. Now we have all the angles of the Earth-Moon triangle, and we know the length of one side. Simple geometry gives us the rest. Our parallax calculation gives us 364,480 kilometers to the moon. With just over 1.6 kilometers in a mile, that comes to 226,477 miles. Of course, the moon travels in an elliptical orbit around the Earth, so its distance varies. Here's how different full moons look between the closest and furthest points. It's important to note that once you know the distance, there are a number of other things we can learn about an object. For example, given the distance and the angular displacement of the object in the sky, we can calculate its size. Here we see the moon's diameter is almost 3,500 kilometers. That's just over 2,000 miles. Mars is our second closest neighbor next to Venus, and our spacecraft and landers have explored it in great detail. Iron oxide in the dirt and rocks gives the planet a reddish color. It's tilted like the Earth, giving it seasons. Olympus Mons, its biggest mountain, is 3 times higher than Mount Everest. And Valles Marineris, its giant gorge, is 3 times longer than the Grand Canyon. On May 12, 2016, the Hubble Space Telescope captured this striking image of Mars. The planet was 80.5 million kilometers from Earth. This observation was made just a few days before Mars' opposition on May 22nd, when the Sun and Mars were on exact opposite sides of the Earth. This phenomenon is a result of the difference in orbital periods between Earth's and Mars' orbit. While Earth takes 365 days to travel once around the Sun, Mars takes 687. As a result, Earth makes almost 2 full orbits in the time it takes Mars to make just one, resulting in a Martian opposition about every 26 months. The next one will be on July 27, 2018. Given that the orbits of Mars and Earth are ellipses, and their orbital velocities are different, the distance between the two can vary from 55 to 402 million kilometers. That's 34 to 250 million miles. Back in 2003, the two planets reached a near minimum distance of 56 million kilometers. The last time that they were that close was over 50,000 years ago. Rather than list all the ranges of distances between the Earth and the various planets, a good way to report planetary distance is to use an average distance from the Sun. An astronomical unit, AU for short, is the average distance from the Earth to the Sun. That's 150 million kilometers, or 93 million miles. We'll cover a way to measure AU in our segment on the Sun. Mars is 1.5 AU, or 228 million kilometers from the Sun. That's 142 million miles. Mars has two small moons, Phobos and Deimos. The moons appear to have surface material similar to many asteroids in the outer asteroid belt, which we'll cover shortly. This leads most scientists to believe that both moons are captured asteroids. Here are the distances to the other planets in our solar system. Mercury, a hot, cracked rock not much bigger than the Moon, is only 58 million kilometers from the Sun. That's 36 million miles. Its daytime surface temperature is 430 degrees Celsius. That's 800 degrees Fahrenheit. That's hot enough to melt lead. Mercury has no moons. Venus, with its sulfuric acid atmosphere, is 108 million kilometers from the Sun. That's 67 million miles. It's around 80% of the size of the Earth and as hot as Mercury. This ultraviolet view of the planet's clouds was taken by the Pioneer Venus probe in 1979. The probe found that, like Mercury, Venus has no moons. Jupiter, the largest planet by far, is 778 million kilometers from the Sun. That's 483 million miles. Its mass is 317 times greater than the Earth. It is the giant solar system vacuum cleaner, eating up the Sun's early debris to become larger than all the rest of the planets combined. Scientists think Jupiter has at least 69 moons. The most interesting are the 4 discovered by Galileo: Ganymede, Callisto, Io, and Europa. Ganymede is the largest moon in the solar system and is the only moon known to have its own internally generated magnetic field. Callisto's surface is extremely heavily cratered and ancient, a visible record of events from the early history of the solar system. Io is the most volcanically active body in the solar system. As Io travels in its orbit, Jupiter's immense gravity causes huge tides in the solid surface, like our moon affects the oceans. This generates the heat for the volcanic activity. Europa's surface is mostly water ice, and there is evidence that it may be covering an ocean of water. It is thought to have twice as much water as we have here on Earth. This water, along with subterranean volcanoes, may have created a zone where life can form. Saturn, with its beautiful rings, is 1.4 billion kilometers from the Sun. That's 886 million miles. Its mass is 95 times greater than the Earth. The Cassini probe has been taking pictures of the planet, its rings and moons, for 13 years. Saturn has at least 62 moons, and every one of them have been probed by the Cassini spacecraft. Here are 2 of them. Titan is the largest. It is the only moon in the solar system known to have a significant atmosphere. Enceladus has more than 100 water geysers at its south pole, from a subterranean ocean that may be friendly to life. Saturn's rings are absolutely beautiful. There are billions of particles in the entire ring system, ranging in size from tiny dust-sized icy grains to a few particles as large as mountains. It is about 1 kilometer thick and ranges out to 282,000 kilometers from the center of the planet. That's about 3/4 the distance between the Earth and the Moon. This Cassini image shows a portion of the inner central part of the planet's B ring. Cassini ended its mission on September 17, 2017, with a plunge into Saturn's atmosphere. Uranus, with its extremely cold hydrogen and helium atmosphere, is 3 billion kilometers from the Sun. That's 1.8 billion miles. Its mass is 14 times greater than the Earth. Uranus has 27 known moons. The largest are Oberon and Titania. They were photographed by Voyager 2, the only spacecraft to ever visit Uranus. Neptune, a twin of Uranus, is the furthest planet from the Sun at 4.5 billion kilometers. That's 2.8 billion miles. It takes 164 years to revolve around the Sun. Neptune has 13 moons that we know of. Triton is the largest. It has ice volcanoes that sprout what is thought to be a mixture of liquid nitrogen, methane, and dust, which instantly freezes and then snows back down to the surface. In addition to the 8 main planets in our solar system, there are a number of large bodies too small to clear the debris in their orbit. These are called minor or dwarf planets. We know of 5, but there could be dozens more. Here are 3 of them. Pluto, with its methane ice surface, is out in the Kuiper Belt at 7.5 billion kilometers. That's 4.7 billion miles from the Sun. At that distance, it takes almost 250 years for one revolution. Pluto is 450 times smaller than the Earth. It was reclassified as a dwarf planet in 2006 when other objects its size were discovered. Charon is the largest of Pluto's 5 moons. With an unexpectedly interesting surface, it is half the size of Pluto. This photograph was taken by the New Horizons spacecraft in 2015. Ceres, the only dwarf planet in the asteroid belt, is 414 million kilometers. That's 257 million miles from the Sun. It was discovered in 1801 and classified as an asteroid. Once the Dawn spacecraft entered orbit around Ceres in 2015, and its true size was understood, it was reclassified as a dwarf planet. Its diameter is approximately 945 kilometers, or 587 miles, making it around 14 times smaller than Pluto. Makemake was discovered in 2005 by a team at the Palomar Observatory. It is in the Kuiper Belt at 7.8 billion kilometers, or 4.8 billion miles. It is thought that Makemake's reddish-brown color comes from a layer of methane at its surface. Asteroids are relatively small, rocky worlds that revolve in elliptical orbits around the Sun. There are billions of them in the solar system, ranging in size from a few meters across to the size of dwarf planets. Asteroids have remained mostly unchanged for billions of years, so research into them could reveal a great deal about the early solar system. To that end, a probe called OSIRIS-REx, launched in September 2016, will travel to a near-Earth asteroid called Bennu and bring a small sample back to Earth for study. If all goes as planned, the spacecraft will reach Bennu in 2018 and return a sample to Earth in 2023. Most asteroids lie in a vast ring between the orbits of Mars and Jupiter, called the Asteroid Belt. It ranges from 2.2 astronomical units to 3.2 astronomical units from the Sun, and is around 1 million kilometers thick. It's estimated to contain around 30 billion asteroids larger than 100 meters across. But the entire mass of the asteroid belt comes to little more than 4% of the mass of our Moon, with Ceres accounting for almost half of that. But with as many as 30 billion asteroids in the belt, it is interesting to calculate the average volume of space each one has around it. Although the density varies, we can get an average by dividing the asteroid belt volume by the number of asteroids. We get 12.7 trillion cubic kilometers of space for each asteroid. That's 3 trillion cubic miles. If we went there, it would look quite empty. So navigating through the belt would be easy, and collisions would be rare. But we do know that lots of asteroids exist outside the asteroid belt. For example, the outer moons of the giant gas planets are all thought to be captured asteroids. And asteroids also orbit gravitational volumes known as Lagrange points. In 1772, French mathematician Louis Lagrange discovered 5 points around orbiting objects where gravitational and centripetal forces cancel themselves out. L1, L2, and L3 are on the line connecting the two bodies. They are unstable. That means it takes a small amount of work to maintain an orbit at or around these points. L4 and L5 are on the orbital path of the smaller body. They are found by using equilateral triangles. They are stable, and Lagrange claimed that small objects could orbit these Lagrange points. 134 years later, between 1906 and 1908, 4 such minor planets were found around Jupiter's L4 and L5 Lagrange points. Asteroids at Lagrange points are called Trojans. As of May 2017, we know Jupiter has at least 6,515 Trojans. Such objects have also been observed in the orbits of Mars, Neptune, and several moons of Saturn. In 2010, we discovered a Trojan asteroid orbiting Earth's L4 point, 60 degrees ahead of the Earth, called 2010 TK7. Here we see an animation of 2010 TK7's orbit. The clock shows how the orbit changes over time. Over the next 10,000 years, it will not approach Earth any closer than 20 million kilometers. That's 50 times further away than the Moon. Our space program takes advantage of these points when we position satellites to observe the Sun. Here we see that L2, where the James Webb Space Telescope will orbit, is 4 times further away from us than the Moon. We'll cover this a bit more in our section on the heliosphere. The Sun is the final object we'll cover. It defines the entire solar system. But figuring out how far away it is difficult. This is because we cannot see any nearby stars for parallax measurements. The Sun is just too bright. But total eclipses and passages of Venus across the face of the Sun as viewed from Earth have enabled excellent measurements. Here is a method that uses parallax to find the distance to Venus, that in turn enables us to triangulate the distance to the Sun. Let's look at the motion of Venus in the sky relative to the Earth. As Venus orbits the Sun, it gets further away from the Sun in the sky, reaches a maximum separation from the Sun, corresponding to the greatest elongation, and then starts going towards the Sun again. By making observations of Venus in the sky, one can determine the point of greatest elongation. At this point, the distance between the Earth and Venus can be determined by a parallax at 104 million kilometers, or 64.6 million miles. The line joining Earth and Venus will be tangential to the orbit of Venus. Therefore, a line from Venus to the Sun at this point of greatest elongation is 90 degrees from the line between Earth and Venus. Drawing the line between the Earth and the Sun fills out the triangle. We call the length of this line, that represents the distance between the Earth and the Sun, an astronomical unit, or AU for short. The angle at the Earth is easily measured, 46.1 degrees. Now, using trigonometry, one can determine the distance, 150 million kilometers, or 93 million miles. Once the distance between the Earth and Sun is known, one can calculate a number of other parameters. We know that the Sun subtends an angle of just about 1/2 degree. As we did with the Moon, we can calculate the diameter of the Sun at 1.4 million kilometers, or 860,000 miles. The surface area at 6.16 trillion square kilometers, and the volume at 1,440,000 trillion cubic kilometers, or 330,000 trillion cubic miles. The Earth's orbit is very close to circular, so with the Earth's orbital radius around the Sun being 150 million kilometers, the distance traveled in a year is the circumference of the circle. That's 942 million kilometers, or 584 million miles. Dividing by the number of hours in a year, we get the velocity of the Earth around the Sun, 107,500 kilometers per hour. That's 66,700 miles per hour. Now, with the distance to the Sun and our velocity around the Sun known, we can use Newton's equations to calculate the mass of the Sun at 2,000 trillion tons. In fact, the Sun is 99.98% of the mass of the entire solar system. So as vast as our planet is, over 1 million Earths can fit into the Sun. So, how long does it take light from this magnificent Sun to reach the Earth? Until early in the 18th century, it was generally believed that the speed of light was infinite. This view was held by Aristotle in ancient Greece and vigorously argued by the French philosopher Descartes, and agreed to by almost all the major thinkers for over 2,000 years. Galileo was an exception, but when he tried to measure the speed of light, he failed. Light was either too fast or possibly infinite, was his conclusion. But Galileo did set the stage for the first measurement. After he discovered the first 4 moons of Jupiter, he suggested that the eclipse of the moon Io would make a good celestial clock that navigators could use to help determine their location. In 1676, the Danish astronomer Ole Romer was compiling extensive observations of the orbit of Jupiter's moon Io to see if Galileo was correct. The satellite is eclipsed by Jupiter once every orbit. Timing these eclipses over many years, Romer noticed something peculiar. The time interval between successive eclipses became steadily shorter as the Earth in its orbit moved towards Jupiter, and became steadily longer as the Earth moved away from Jupiter. In a brilliant insight, he realized that the time difference must be due to the finite speed of light. That is, light from the Jupiter system has to travel further to reach the Earth when the 2 planets are on opposite sides of the Sun than when they are closer together. Using what he knew about planetary orbits from Kepler, he estimated that light required 22 minutes to cross the diameter of the Earth's orbit. The speed of light could then be found by dividing the diameter of the Earth's orbit by the time difference. The actual math was done by others after Romer's death in the early 1700s. Those who did the first arithmetic found a value for the speed of light to be 227,000 kilometers per second, or 141,000 miles per second. Not too bad for instruments of the 18th century, The modern value is 300,000 kilometers per second, or 186,000 miles per second, as determined by bouncing laser light off the moon. To answer our question about how long it takes light from the sun to reach the Earth, we simply divide the 150 million kilometers to the sun by 300,000 kilometers per second to get 500 seconds. That's equal to 8.3 minutes. In this segment, we built the second rung of our distance ladder, parallax. We can now use the diameter of the orbit of the Earth around the Sun as our baseline, 300 million kilometers. That's 186 million miles. Combined with the direct measurement and geometry from the first rung, we are set to measure distances to the stars. But first, we'll close out our chapter on the solar system by taking a look at the heliosphere, Kuiper belt, Oort cloud, and comets.